So we'll start with Ashish. Ashish, please start.
So, hello everyone. Today I will be talking about the work that I did in my PhD. I'm Ashish, and in my PhD I mostly work with Professor Jasheet Singh Bagla at Ismahali. Currently, I'm a postdoc in Ben Gurion University of Negev, Israel, working with Abizadrin. So, before starting the talk, let me thank IAGRG Council for giving me this opportunity to present my work at the IAGRG. This session of IGRG. So in my thesis, I mostly worked in strong gravitational lensing. My thesis can be divided, is based on these 4 publications and can be divided into 2 parts. In the first part of my thesis, we studied the singularities in gravitational lensing. And in other part, we studied the gravitational lensing of gravitational waves. In today's talk, due to the time constraints, I will not talk about the gravitational lensing of gravitational waves. I believe you already heard a little bit about that from Anupata's talk. I will only talk about the finding singularity in gravitational lensing and how they are important and something like related stuff. Okay, and apart from that, we also worked on other stuff in my PhD. These are the other 4 publications, and these are not part of the thesis. So again, I will not be talking about any of these. So so let's start. So as I mentioned, in my PhD thesis, I mostly worked on strong gravitational lensing. So whenever I say gravitational lensing, I mean strong gravitational lensing. So the first question is, what is gravitational lensing? So a basic idea of gravitational lensing is that you have a source, and which is emitting, let's say, light, and we are here, or our telescope, and we are trying to observe these distant sources. So if we have some mass distribution sitting in between us and the source, then what will happen that the light that is emitted from the source will experience a deflection when it passes nearby this mass distribution. Here it is a galaxy, but it could be a galaxy cluster, a group of galaxies, or something else. And because of that, we don't see the actual source, the unlensed source position. Instead, what we see the lens, and we see multiple images of the background source. So this is what the telescope is going to see. This is the lens galaxy, and these 2 are the lensed images of the background source. So this is a schematic diagram, but in actual observations, what we see, we can, depending on the lens mass distribution and the lens geometry, we can see ring-like structures. We can see quad image formations. Here you see this yellow dot. This is the lens, this intermediate mass distribution, and you see these 4 dots around this yellow dot, and these are the 4 images of the background source. Or we can even observe a smiley face in the sky, and where these 2 yellow galaxies are the lens galaxies, and this arc-like structure, they are the background galaxy, which is strongly lensed. Now, in order to study gravitational lensing, we use something called the lens equation, which relates the unlensed source position, which is beta, with the lensed source position or the image position that we observe, which is theta, and it also has this deflection angle. This deflection angle basically quantifies or tells you how much the light is going to deflect it when it passes near the lens. And this deflection is a deflection angle depends on the lens mass distribution, what type of lens mass distribution you have, and or the lens potential. Now we can study the lens equation in more detail using the Jacobian, which is defined something like this. And as you can see here, it depends on the second derivative. Either you can write it in terms of a deflection angle or in terms of lens potential. Now, one of the property of strong gravitational lensing is it can actually magnify the background sources. And the magnification factor by a source can be magnified is defined something like this, which is inverse of the determinant of the Jacobian. Now, as you can see from here, that first, now the kappa and gamma are some combination of the second derivative of the lens potential. And for some particular combination of kappa and gamma, this term can vanish. And wherever this term is going to vanish, you will see an infinite magnification. And that particular point is known as singularity of the lens mapping. And so here you see kappa and gamma depends on the lens mass distribution, and we are only focusing here right now. We are focusing on the lens plane. Okay. Now, if we have a simple lens mass distribution, for example, like an elliptical lens mass distribution, then if we locate all the points where mu is infinite, then we will have this red curve. And in lens plane, we call them critical curves. And if we map them back into the source plane using the lens equation, we get this green curve, which is a diamond-shaped curve made of smooth segments joined together at these cusp points. And if we make the lens more complicated, then you see that the critical curves gets complicated, and these green lines are known as caustics. So they are counterparts of critical curves in the source plane. And if a source lies near them, then it will be highly magnified by default. In principle, the magnification is infinite at these lines, but in reality, we do not observe that because of the finite source size and other effects. But from here, you can get idea that if your lens mass distribution is more complicated, you will have more complicated geometries. Now, as I showed in the last section, in the last slide, that typically for a simple elliptical lens mass distribution, you have this type of smooth segments joined at the cusp points. Now here, I fix the lens, all the properties of the lens, and I only vary the source redshift. So basically, I'm moving the source away from us. So you see that the fold and cusp are present for all source redshifts. And so they are known as stable singularities, and they are present for all source redshifts and strong gravitational lensing. There are something called unstable singularities also, like swallowtail purse pyramids. And they are only present for specific geometries in a given lens system. They are highly sensitive to your lens mass distribution and other parameters. And now the question is, how do you find them? Because these are very sensitive to all these lens parameters. So all these singularities have this thing in common, that they follow the cusp positions. So you actually look for cusps, these cusp-like features here. And now the question is, why do you want to study all of these unstable singularities? They are rare, so they will be less in numbers, but why do you want to study them? So earlier works, in 2009, there was a work, and that suggested that you should only observe one or two such image formations near these unstable singularities. So we wanted to test this, and so for that, what we did our analysis. But before that, I want to give an example. For example, as I said here, that purse is an unstable singularity. Now, these unstable singularities comes with a characteristic image formation. For example, in case of purse, you see this ring-like image formation. So far in observations, we have observed one ring-like image formation in Abel 1703, and we know that this is near the purse singularity. Now, according to Zivri and Marshall, this should be the only image formation that we should observe in the all-sky surveys. Okay, and we wanted to test this. So what we did, first we developed an algorithm to locate all the unstable singularity or point singularity that a lens has to offer. Then we located all the singularities for, we validated our algorithm using ideal lenses, simulated lenses, and real lenses. And once we have the algorithm, the next question was, okay, now we are in a position to estimate what is the cross section what is the cross section of observing these type of image formations in the all sky surveys and like the all sky surveys. So what we did, we took Hubble frontier field clusters, which are very well studied sample of 6 clusters, and we estimated what is the cross section using both parametric and non-parametric methods. And what we find is that non-parametric method gives you minimum number of these point singularities, and if you estimate the cross section corresponding to non-parametric lens mass models, what you are going to get, you will get that one cluster in every 5 clusters should give you one image formation near purse-like image formations near purse singularity. So remember, earlier the Zivri Marshall, their paper said that you should observe one in all sky, but we say that one in every 5 clusters. So that's a huge difference. And after that, we folded. Now the point is that in lensing by clusters, you don't have like a lot of image formations. With JWST, the number is increasing, but still, you don't have a unique lens mass model. You actually have a range of mass models that fits your data. So how this statistical uncertainty in your lens parameters is going to affect this one in every 5 clusters, this number. So we again use the non-parametric mass models because that gives us the lower limit. And then we again studied how these statistical uncertainties are going to affect our estimates. So we find that the best fit mass models again gives the lower limit, even if you fold in the statistical uncertainties. And because, as I told you, that if you want to find these unstable singularities, you look for cusp. So we know how many cusp a source is going to give you at each and every source redshifts. So we can also estimate how many image formation near cusp you are going to get. So we also estimated that number in this paper.
Ashish, you have 1 minute.
And all these calculations were done using HFF clusters and for galaxy luminosity function that is suitable for JWST.
Ashish, you have 1 minute.
Okay, thank you. So with that, this is what we did in our thesis, and finally I summarized that we developed an algorithm to locate all these point singularities. Then we say that we should observe one pulse-like image formation in every 5 clusters, which is much more than what was earlier estimated. And this number, 1 in every 5 cluster, it's valid even if you fold in statistical uncertainties. Now the interesting thing came to our attention this year in March, when we got a mail and somebody told us that we actually observed 8 to 10 new image formations near Perth. So earlier we only had 1. Now we have around 10 image formation near Perth, which is what we are saying in our thesis. So we are actually continuously working on these unstable singularities and how can we use them to study more about the clusters. And with that, thank you very much for listening to my talk.
Thank you very much, Ashish, for this very nice talk. The floor is open for questions. Starting from the referees, any? Okay, I will start with one question. So, Ashish, you said this number of images essentially depends on your the reconstruction model that you used. So, how robust is the conclusions then?
Okay, so first of all, I'm not able to hear you very clearly, so I don't know what you are asking. Sorry about that.
So you mentioned that the number of images number of singularities that you get depends on the mass model and your algorithm that you're using. So how robust will be the conclusions then?
How robust these conclusions are, that's what you are saying? One in every 5 clusters?
If you go to 2 slides before, you said if you use a parameterized model and non-parametric model, you get different number of...
So here?
The previous...
Yeah, okay, so this is for a single cluster. Let me show you this slide again. So this is Abel 370. So these are 4 different mass models, and these green and red lines are A3 lines, something called. And if you estimate the number of point singularities or unstable singularities using the parametric mass models, you'll see a lot of much more point singularities or unstable singularities compared to Williams mass model, which is non-parametric. So we said that we will work with the lower limit. So we are actually focusing on the lower limit that we're actually, for all these models. So it's pretty robust in that sense, because we are not overestimating. If there is anything, we are actually underestimating in our numbers.
I see. Thank you. Okay. Surhud, yeah.
Hi, Ashish. Surhud here. I wanted to ask whether you have finally figured out what was the problem regarding the abundances that were calculated in the previous paper, why they were getting lower abundances compared to you?
Yeah, so actually, you are talking about this particular point, like why we are getting the high number compared to the Zivri and Marshall paper. So actually, yes, that's a good question. And the same question was asked to us by a referee also. And we looked into that paper, and there was not much of a detail so that we can actually, work out their numbers. So I think it's related to what type of lens mass distribution you are using to estimate, because first thing, you need elliptical lens mass distribution. And if you are using very simple lens mass distribution, which has less ellipticity, then what will happen that you are going to significantly, underestimate the cross section. So that might be a reason. I don't know the exact reason, because there was not a lot of details in their paper.
So did they also consider clusters, or was it only elliptical galaxies or something with
Yeah,
satellites around them.
Yeah, so they did the estimate for both clusters and galaxy scale lenses. And even in clusters and group scale lenses, they say that you should only observe one pulse-like image formation in the whole sky survey.
So
and
is there
honestly,
any
like, I didn't know.
Yeah, is there any dependence on the depth of the survey that you consider, or where they consider something like LSST versus you were looking at HST data, etc.?
Yeah, that might be a reason. If they are looking into a shallower data, then they will have less number of source galaxies that can give you this type of image formation. That might be a reason. So as I told you, I did not see a lot of details in the paper, so I wasn't able to, work out their numbers properly.
Okay, thank you, Ashish, for this very nice talk. We must continue.
Yeah,
so,
I will.
Yeah.
Thank you.
Ruchika, you are the next. Could you please try sharing your screen?
Yes. Let me just do that. Is it visible?
Not yet. Yes, it's coming. Something is coming up. Can you go? Okay, we can see your slides. Please go ahead. You have 12 minutes. We'll give you 10 minutes warning.
Okay, maybe. Maybe I can stop my video and bandwidth will increase. Is it coming now?
Yes.
Can I start?
Start. Please start.
Hello. Okay. Yeah. Hello everyone. Today I'll be talking about universe. Universe is really big, but today I'll be just talking about some of the very significant works that I did during my PhD. And the title of my talk is Some Aspects of Expanding Universe. That is also my thesis title. And before starting, I would really like to thank the organizers of IAGRG for giving me this excellent opportunity to highlight my work and to talk about it. And then I welcome you all for next 15 minutes. I did my PhD at Center for Theoretical Physics, Jamia Millia Islamia, New Delhi, under the supervision of Professor Ranjan Ananda Singh. Currently, I am at La Sapienza University of Rome, Italy. So this is the picture of our universe, and this diagram shows the evolution of the universe all the way from Big Bang. So the extreme left is the Big Bang, and then we have accelerated expansion, which is also known as inflation. After 375,000 years, we have cosmic microwave background, where the first light is coming from us, and then then it is followed by dark ages. After around 400 million years, we have the first star formation, and then there is development of galaxies, planet, etc. And in the very later stage, we have accelerated expansion due to the presence of dark energy. Now, the universe have been expanding forever, and we are actually interested in knowing how the expansion is happening from CMB to at present. Now, what is the way to measure the expansion of universe? So one way is we can see the observation, and the other way is we can try to match it with the theory. We have made quite a progress in observational upfront. Like we are having ground and space-based telescopes in working in various frequency ranges from microwave, ultraviolet, or optical ranges, and also UV. So namely the telescopes are Planck, WMAP, SCA, GMRT, Hubble Space Telescope, Gaia, JWST. Also, we have many theoretical models trying to explain the observable universe, including modified gravity models, modified matter models, parameterization models. But the most simple and the most favored model by the observation is Lambda CDM model. So this is how the Hubble parameter for Lambda CDMs looks like. So this H is the Hubble parameter, which tells about the expansion of the universe. H0 is the Hubble parameter at present. And then we have omega m0, which is the matter density at present. This is how it evolves with redshift. And then we have omega r0, which is the radiation density at present. And then finally, this is the dark energy, which is responsible for the accelerated expansion at present. So this is how Lambda CDM model looks like. And for the theory to work, it should match with the observations. But the present scenario is that when we are trying to measure this expansion rate using the cosmic microwave background, we are getting the value of Hubble constant to be 67.4 plus minus 0.5 kilometer per second per megaparsec. But on the other hand, when we are trying to measure the same expansion rate, same parameter, Hubble constant, using the late universe, using local measurements or cosmic distance ladder, using Hubble Space Telescopes or Gaia, we are getting the value of H naught to be 73.04 plus minus 1.04 kilometer per second per megaparsec. And these two values of the same parameter, Hubble constant, is more than 5 sigma away. Now the main difference while calculating or while deriving this parameter Hubble constant is when we are trying to measure this value using cosmic microwave background, we assume a model, we assume a theoretical model which is Lambda CDM. On the other hand, when we are trying to measure the same expansion rate using the local measurements, we are not assuming any cosmological model, though we have some astrophysical assumptions. So the main intuition that comes here that tries to explain this tension is maybe the theoretical model that we are using here, that is wrong. So this is the main motivation of my work. So this was the basic overview. For the theory to work, it should match with the observational result. But since it does not match and it shows tension, so during my PhD, I tried to find the best theoretical model to fit all the observational signatures. I also tried to study the observational data set and I tried to see which data set gives the tension. I tried to solve the ongoing tensions between the theory and observation, including the Hubble tension. So this is one of my work during the PhD. I tried to find which present theoretical model best explains the observational data set. We used 21 dark energy models, including canonical scalar field models, non-canonical scalar field models, Galilean models, and dark energy parametrization models. We used numerous data sets, including the very early universe cosmic microwave background and local Hubble constant value from shoes, along with all the data sets in between from baryon-acoustic oscillations, time delay strong lensing, cosmic chronometers, supernova type A, and growth measurements. We compared all of these models using the Bayesian evidence analysis. The important point about Bayesian evidence analysis is that it compares different models irrespective of the number of parameters. It marginalizes over the parameter space, so we can directly compare different models without thinking about how many number of parameters they are having. So this is the one of the result of our paper. On the x-axis, we are having 21 dark energy models which we are comparing. On the y-axis, we have log evidence. The black horizontal line on this plot is about Lambda CDM. The models which are lower than this line are disfavored that Lambda CDM. But on the other hand, the models on above this line are favored than Lambda CDM, and we tell how much favored they are using Jeffrey scale. So if the difference in log z is between 1 and 2.5, then it means these models are significantly doing better than Lambda CDM. So all these star models which are having denoted by star, they are doing significantly better than Lambda CDM. So in this particular work, we benchmark all the theoretical models that are preferred over Lambda CDM with significant evidence. So in this work, we created, we tried to put benchmark on which models are preferred better than Lambda CDM. So anybody looking after this work can simply take the models which are better than Lambda CDM and simply can work on this. So it appeared in PRD in 2018. Then the second work, before that I would try to explain that we took 21 dark energy models including Lambda CDM, but then also the tension still remains, which is more than 5 sigma. So rather than taking the more theoretical models, we tried to build a model-independent approach, model-independent reconstruction using pad approximation. And we try to see if the model-independent approach agrees with any of the present theoretical behaviors. So the plot here we see is on the x-axis we have redshift going up to the redshift 2. On the y-axis we have effective equation of state. Magenta line is our reconstruction. The red line is the Planck reconstruction. The black horizontal line is denotes -1/3. So the region below this horizontal line tells us about the accelerating universe, and the above it means it is deaccelerating. So at present we can see both the reconstructions from Planck and from ours shows the accelerating kind of behavior. But then after the redshift of 0.5 goes to deaccelerated region for both of them. But after redshift of 1.5 we see that there is a possibility of accelerating universe again. We did many reconstructions after that, and also when we tried to do the reconstruction of equation of state for dark energy, we could confirm that at present we are having phantom behavior which is supported by the cosmological data. Also, we confirmed the Zhao et al. Nature paper results, which shows that there is a phantom to non-phantom crossing. And using many other reconstruction and using this reconstruction, we could also say that no particular dark energy behavior is consistent with entire redshift range from 0 to 2, though it may match with Lambda CDM or any other model in certain redshift ranges. But from 0 to 2 entire redshift range, just no present dark energy behavior is able to retrace the whole behavior. So this paper appeared in MNRS in 2019. In continuation with this work, while doing the model-independent reconstruction, we also find that there is a possibility and signatures of negative cosmological constant, and it is consistent with the cosmological data. So
Ruchika,
this
you have,
plot
1 minute.
is on the x-axis we have redshift. On the y-axis we have
Ruchika, you
Hz
have
upon
1 minute
plus.
to go.
Okay, yeah, sure. On the y-axis we have Hz upon 1 plus z. So we can see here, and this green line is the Planck reconstruction, the red one is ours. So we can see when we are trying to build this behavior and trying to explain the negative cosmological constant, this is completely retracing the behavior of Planck along with the BAO Bose data and DR14 quasars data. So this was the first time there was observational signatures for presence of negative cosmological constant. And it also shows that the presence of more massive galaxies at higher redshift than standard model at Lambda CDM. This can be seen in the plot at the right side. So this red dot represents the omega matter density, and the green dot represents the dark energy density. So this red one we can see around, at present it is 0.3, but when we go to the redshift 4, it is more than 1. So it shows the presence of more massive galaxies at higher redshift than Lambda CDM. So this paper appeared in 2020, and after doing this work, there are many studies which show the similar kind of result and prefers negative cosmological constant. So the takeaway is, did we solve the big question that we started with? Did we resolve the Hubble tension, or were we able to find the best theoretical model describing the evolution of universe? The answer is no. But we could motivate negative cosmological constant models, cosmological model independent methods, early dark energy methods, and we could also confirm many present results. And it is significant because it still remains open question, but the work we did is significant because it does not end there. At present, I'm working on allowing G transition at lower redshift can actually resolve the Hubble tension and investigating current tension between cosmological data and their impact on fundamental physics using JWST dataset. And it would be incomplete if I don't acknowledge my collaborators and who helped me learn this subject, and of course my supervisor. So these are the references of the works that I did during my PhD. If you want to know in big detail, then this is my email ID. Thank you.
Thank you, Ruchika, for this very clear presentation. Floor is open for questions. Go on, yes. in slide number 13.
Okay. Slide number 13.
So when you mean model independent reconstruction, so model independent mean your you are independent of the matter model. Like gravity is still Einstein's gravity and the metric is still FW.
I could not understand. Can you please repeat?
So your gravity theory is GR and the metric is FRW. Yes.
So, sorry, we used a reconstruction method here. So when we are using Hubble parameter there, Hubble parameter you can also write as A dot by A, right? And then we try to write the Hubble parameter in different derivatives of scale factor. So you can say it is like Taylor expansion,
Yeah,
but Taylor is like
it's still
a polynomial, and Pett approximation is in numerator and denominator we are having two different polynomials. So this is PADE 2 that we used.
So it should be still FRW, right? Because
it is kind of reconstruction, I would say. Like we are not assuming a FLRW.
Yeah.
So Ruchika, I had a question. Okay, okay. So, yeah, no, go on.
Okay. Ruchika, one of the questions that I had was, like it is unclear which data sets you are using exactly, and given that you don't resolve the Hubble tension, in which data sets do you actually get the improvement? Because you are getting better evidence values, so there must be some data which is being fit better. So if you can clarify that, that would be great.
Yes. Okay. So here we are using baryon acoustic oscillation, time delay strong lensing, H naught, and cosmic chronometers HZ, supernova, CMB, and growth in this picture, in this plot. But in the paper we have different combination of data sets, and we have compared different models. But in all of them we could see that the scalar field models are better preferred than Lambda CDM.
But could you explain which data is driving it?
Which data will drive?
Which data is driving you to these conclusions?
So,
is there a specific data set which?
I can explain at looking at that paper better, like in that sense. But I guess it is more related with the models that we are using, and data's, changing the data sets, the result does not change much. Adding some particular data or removing some particular of data, that does not change much, but changing the models actually.
Yeah, but it would be good to see exactly which observables are being fit better in these models compared to the Lambda CDM.
Oh, okay. I don't know if I have.
Yeah, I guess Surhud is alluding that if you just use a CMB,
I can see into the paper and tell you. I don't remember exactly.
I guess Surhud is saying if you just use a CMB, presumably the Lambda CDM would come up as the top, because that is what is at least shown by the official Planck analysis and so on. Now you are drawing a different conclusion. So which data set is driving this result? Yeah, we can discuss it. I have a general question about the Bayesian inference also. So indeed, this it marginal it compensates for it sort of, or it puts the penalizes for introducing extra parameters, but your evidence value still depends on the priors that you put on the extra parameters, right? So for example, you can get different evidences depending on the choice of priors that you put on the extra parameters. So have you looked at, for example, is there a robust way of putting priors on your scalar field parameters, or have you checked the robustness of the results with respect to the choice of priors?
Can you please speak slow? I could not get you,
okay.
Maybe because
so
of
your
time.
Bayesian evidence can depend on the choice of priors that you put in your extra parameters. Right?
Yes, it will depend, but we have used the very uniform priors, so it should not change the result.
But
I
then
mean,
the uniform prior in certain region, right? So you can put uniform priors with different cutoffs. So for example, does the result change
so
if you change the cutoff value for that uniform prior?
So, I mean, we have not taken the cutoff to infinity plus infinity minus infinity. We have given some physical values to that. But even if we change the priors, right, 2 plus infinity or minus infinity, if it is physical, it would not change the result. That
Okay.
is something I meant by uniform priors.
Okay,
Yeah.
thank you. Okay, so we'll continue. Thank you, Rujika, for this very nice talk. And we'll continue. The next talk is by Shayak Datta.
Thank you. Thank you, everyone.